So these techniques that we've talked about now, Euler's method and Heinz method, we've applied it to a 0D problem. This allows us to step forward in time and develop a temperature solution where we assume that the temperature inside the domain is uniform, right? This is the 0D assumption. Now let's take these same ideas and apply them to 1D 1D conduction problems that are transient, right? This is where we ran into the roadblock with the analytical solutions. We got to this differential equation that was really difficult to solve beyond this class, and so we don't know how to proceed. Now we can take the numerical approach where we just have these sort of approximate resistance-based algebraic solutions, apply them, and solve these otherwise really difficult problems. So let's extend this to the 1D numerical solution. Let's look at a problem where we have the following going on. So on the left-hand side of the domain, where time is less than 0, so before the simulation starts, we have the entire system at this temperature T initial, right? And then once time hits 0 and then into our simulation time, we're forcing that the left-hand side of this domain go to TH. On the right-hand side, we are holding this at TC, the entire simulation, and we're also just noting that the cross-sectional area is this value AC. Our domain goes from x equals 0 to L, and then we have this adiabatic boundary on the top and on the bottom, which means that heat only will flow in the plus or minus x direction, right? So then we've discretized the domain, just as we did for the 1D steady state numerical solution, into a bunch of nodes. So node 1, node 2, let me just write this out. So node 1, node 2, node I minus 1, I plus 1. Let's see, this would be, let's call this node M, and let's call this node M minus 1. So this is our problem. So what we're going to do is develop a solution where we do a control volume on the node I, the node 1, and on the node M, right? We're doing boundary conditions, and we're also doing an internal node. So let's start by just noting what the discretization is giving us. So when we discretize the domain, what are we talking about? Well, we actually have two domains, right? We have a space domain and we have a time domain. So our space domain, we're discretizing into these segments delta x, where delta x is equal to L over M minus 1. M is the number of nodes in the x direction. Then our x position xi is equal to delta x times I minus 1 for all I in the set from 1 to M. Those are our xi positions. Our second domain is the time domain. So we have n domains in n nodes in the time domain. So let's compute our time step, delta t. That's going to be the total simulation time, t sim, over n, the number of time steps that we're computing, minus 1. Our time index, or our indexed time variable, t sub j, is going to be delta t times j minus 1 for all j in the set from 1 to n. So we have this double discretization. It's just like the 2D problems that we've gone through, where it's 2D in space, but here we're just discretizing the time dimension instead of the y dimension. So now our job is to look at the control volume around the node I and identify the important stuff there and then do an energy balance. So first let's draw a control volume here. So this is going to be, these lines are halfway between the nodes, right? So the total width of the control volume is, sorry, not D, it's delta X. And then we have stuff going in. Again, because this is a numerical conduction problem, let's draw everything going in, the heat flows. So coming in, we have Q dot from the left. This is coming into node I. Sorry, this is coming into node I. We have Q dot from the right, Q dot R from node I. We also have internal energy change. Right? Inside this control volume, we have some internal energy change with respect to time. So du dt. Right? This is for node I. Now, the way I've done this indexing is kind of incomplete because each of these nodes has this conservation of energy associated with it for both a single node in space and a single time, right? These values are going to change with time. The q dots change with time. Du dt is changing with time. So as we've discretized it, we actually have to add a second index. So it's for the left, it's qi comma j. For the right, it's qi comma j. For du dt, likewise. So we have heat flow that's depending on space and time, and we have internal energy that's depending on space and time. So with all of this, we can go back and do our energy balance and write that out. So let's go on to the next slide here. So let's write out our energy balance. Again, this is for the internal nodes. We would come back and do this for the external nodes as well. So for our internal nodes, keeping track of what we had, we have q dot L ij plus q dot R ij minus du dt ij is equal to 0. Now let's add in rate equations for these things. So giving ourselves rates. So starting with q dot L, right, this is conduction from the left to the right, or conduction from the prior space node to the current space node. So ij, that's going to be, our resistance model is a delta T over a resistance. So this is, ends up being KAC over delta X, right? That's 1 over our resistance. Delta X is the distance we're conducting. KAC is the denominator for that resistance. And then the driving potential here is we're going from left, from the prior node, I minus 1, to the current node I. That's how we've drawn the arrow. So we could say T I minus 1, comma j, minus T I, comma j. So this is our rate equation from the left. From the right, it's going to be very similar. Q dot R ij. That's KAC over delta X again. But in this case, we have Ti plus 1, j minus Ti, j. For du dt, this is going to be the change in internal energy as a function of time. Du dt for ij is equal to rho AC delta x times c times dt I j. So all this stuff is our mass is rho times volume. Volume is AC times delta x. So mass times specific heat C times d temperature d time at node ij. Right, this is going to give us a system of equations. So if we write this out, so let's combine and solve for dt. So why am I solving for dt? Well, remember the goal of this analysis is to come up with a state equation that lets us estimate the derivative that we can then use to step forward in time. All we need is an equation that lets us compute the derivative, and then we can move from one time step to the next. So we've gotten to this point, we combine everything together, and we solve for dt. And this gives us, up here, this gives us the following. So this is dt for ij is equal to KAC over delta x rho AC times delta x times c. So we have delta x is our distance for conduction, rho AC delta x is our mass, c is our specific heat. All this is multiplying these temperatures. So we have Ti minus 1 j we have ti plus 1 j minus 2, run out of room, minus 2 times tij. Right? 2 times tij. So this is our state equation. We can simplify this a little bit further if we just put together the delta x's. Note we've got k over rho c. So actually, just rewriting this out a little more simply, we have dt dt ij is equal to alpha over delta x squared times ti minus 1 j plus ti plus 1 j minus 2 tij. So this here, this is our state equation, as I said. We need the state equation in order to move forward in time. So what we end up doing is we just say, all right, if I'm going to predict tj plus 1, this would be, I guess, using Euler's method. That's actually going to be ti j plus 1. That is the temperature for node I in space at the next time. That's going to be equal to the current temperature for that node at the current time, plus this dt at ij, right, this whole thing here, times our time step, times delta t. So this is going to be, these equations are going to be repeated for all nodes I that are internal. So that's I from 2 up to m minus 1. These are all internal nodes. But we also have for all j from 1 to n minus 1, right? Because we just have to go to n minus 1 to be able to predict the j plus 1th, the last step. Okay, so we repeat this equation for all internal nodes and for all time. And that gives us a set of equations, but we're short on those equations by the end nodes, right? We still need the boundary condition and space nodes in order to finish this up. So we would just kind of repeat this process for the end nodes. And again, it's basically just doing the same energy balance, identifying what's coming from the left, what's coming from the right, and then we know that du dt is also going to change a little bit because you have a slightly different volume, right? You have half the volume. So make sure you account for that. But we just repeat this, and this will give us our system of equations that then we can solve.